efficient.
Okay, why don't we go ahead and get started. As has become now a long-standing tradition, we will have GeoSlam for our first distinguished lecture of spring semester. Those who might be wondering about the origin of that name, it was originally introduced by Dave Chapman before his retirement. He has a son, Jeff, who is an English professor. And so he thought this was kind of like a poetry slam where young poets get up and read their poetry for each other. Anyway, I'm going to turn things over to Gabe to be MC for the slam. But before that, just a couple of announcements. First, Shanna asked me to let you know that GeoSlice is on tonight. Starts today. The other is looking forward. Jim Carter and I have a complete slate now of talks for the spring semester. Next week, our speaker will be Mark Schmitz, who's the director of the Outcrop Geology Lab and professor at Boise State, talking about recent advances in uranium-lead dating and their application to a broad range of geoscience topics. So with that, I'll turn it over to Gabe.
Okay, and I'll pretty quickly here turn it over to our GeoSlammers, I guess. What we call you guys. As always, it's been a real pleasure to work with our incoming graduate students in the reviews class in the fall. We saw a lot of each other. It was fun to kind of see the projects develop. We did a lot of practice presentations of various different types, and each week it was a new thing, and it was just really cool to see. And as a testament to how quickly everybody is moving ahead with their research design and their presentation skills and kind of settling in and developing their programs, when everybody sent me their slides for this talk earlier this week, I looked through them, and almost nothing is the same as it was last fall. So it's going to be a big surprise for me too. In a good way. All right. So SLAM is the poetry slam. That's the model here. But this is impactful stuff we're doing. This is exciting. So we've interspersed a variety of different iconography here that should get you excited about the slam. So we'll start with some roller derby comics and set the stage. So without further ado, we're going to kick it off with Santiago. And here's your first slide. These are going to be short. We've only got 6 of them. So we should be out early for pizza and beverage.
Okay, well, thanks for having me. I'm Santiago. I'm doing my undergrad and my master's at the National University of Mexico, and right now I'm part of the seismic design of Apache. For the first part of my PhD, I will be working in Alaska in this project about getting the seismic velocity structure of the Denali Fault using double beamforming tomography with Amir Alam and Fanchi. So as you know, nearly half of the population in America is exposed to potentially damaging ground shaking, including us here at Utah, and about 30 million people live in areas with high potential to experience damage during an earthquake. These high potential damaging areas are located along the coast, very close to, in California and the state of Washington. This by the Cascadia subduction zone, and this by the San Andreas Fault and the multiple strands. Fault zone structure controls a lot about earthquake mechanics. The hypocenter location, that's the place where earthquakes start, the seismic slip distribution, where the maximum slips occur, and the rupture propagation direction. In this talk, I will focus on strike slip faults, and there are older and younger strike slip faults. In the right side of the screen, you can see this very young strike slip fault. You can think about San Jacinto Fault or Ridgecrest. It's a very broad deformation zone trying to find its way through life. And this is an older fault, like the Denali Fault, with a very focused deformation zone and a very narrow damage zone. In order to study this kind of faults, we have a big scale problem. First, we have the fault core here in the center where all the sheared pulverized rock is, and this in the order of the meters. Then we have the damage zone surrounding this fault core, and this in the order of hundreds of meters. And this damage zone is formed by all the past earthquakes and controls a lot of things about future possible earthquakes. And then to the side we have the extended damage zone, that is where all this elastic deformation happens, and it is in the order of the kilometers. And we have a problem. We don't have enough information. Observations are limited to only a handful of outcrops that have been exhumed from past faults, and we don't know how much have been changed along the way of exhumation. Recent studies from the upper cross, like this one by Wang et al. In 2019, have shown these pretty red, narrower zones that corresponds with the damage zone, and we have seen that it narrows with depth, and this is to the increasing of the normal stresses. And why is important to study these damage zones? Because these damage zones can control a significant proportion of slip during large earthquakes. So what are we going to do about it? We are going to obtain a high 2D model of the Denali fault zone using a linear array. And what do we mean by high resolution? We are going to map the uppermost 200 or 300 meters of the cross with lateral resolution about 10 to 20 meters. 10 to 20 meters, that's pretty high resolution. And we want to understand three main factors. What's the fault zone geometry, what's the extension of the damage zone, and the geological composition of the fault. For this, last spring, we deployed 400 nodes in Alaska, and we are going to use a subset of 90 nodes. Is this line, this is the trace of the Denali fault, and the line is 1.4 kilometers. And we are using these 3-component 5 Hertz nodals. The interstation distance goes from 3 meters to 30 meters, and that's the way we are going to face this very big different scales problem. For the methodology, we are going to use ambient noise cross correlation proposed by Lin, and then we are going to use double beamforming that was proposed by Wang et al. In his PhD thesis, and Wang was our former PhD student of my lab, and we are going to try to get one of these shear wave profile. Why are we going to use double beamforming? Because we have a big problem. When you are trying to map the uppermost cross, we need to use very high frequency waveforms. And in order to get signal from these waveforms pretty scattered, we have to enhance the signal. And double beamforming is a great methodology to do that. And just to wrap up, what we are trying to understand are three main factors: fault zone geometry, extension of damage zone, the geological composition, and this will lead to two things: getting accurately assess the earthquake properties and better estimation of earthquake hazards. Thank you.
All right, we have enough time. We can allow for a question or two. There is one.
So, in terms of Alaska, how damaging can, even if the earthquake can be huge, how damaging can it be compared to Los Angeles?
So you never know, there's different earthquakes, but the last 10 years was a pretty large earthquake in the Denali fault and didn't cause a lot of damage in Alaska, but in California it can be really damaging, and this is a great analog to the San Andreas fault. So we can build up from this Denali array to get stuff in California.
Was there a tsunami with the last earthquake?
No, usually strike slip earthquakes don't generate tsunami.
Aside from hazard as a practical application, what is another sort of first order Earth system process reason why investigating the Denali fault specifically is interesting, either as a seismologist or somebody who just kind of thinks about the Earth generally?
Can you repeat that question, please?
Yeah, so hazard is one thing.
Yeah.
But as opposed to assessing hazard, why is the Denali fault interesting as a first order Earth system?
The Denali fault has been one of the principal faults from scale tectonics in Alaska, so it's pretty important to understand the evolution of the fault, because we can understand big picture what's happening in the North Continental America, and I think it can be greatly used to that.
Cool. Thank you. There's our beat poet. And up next is Hannah Hartley.
Alrighty, so as Gabe said, I'm Hannah Hartley. I did my undergrad at the College of Charleston in South Carolina, and now I am here doing a master's with Carrie Johnson. And I'd like to share with you some of the research I've started working on the sedimentology of Lake Powell. So, if you don't know, Lake Powell is a man-made reservoir in southern Utah. There's the laser right here. So it was created in 1963 when the Colorado River was dammed as part of the Colorado River Storage Project. So its primary purpose as a reservoir is to store all this water for the lower Colorado watershed. So states like California and Arizona where you have a lot of people but not a lot of water. Secondarily, it also creates hydroelectricity for the region as water flows out the bottom, and it's also a popular recreational site. But aside from those very important practical reasons to care about Lake Powell, it's also an incredible scientific opportunity. So as I said, it was dammed in 1963. That means that for its entire 56-year existence, we have a record of what happened in and around Lake Powell. That means inflow, outflow, dry years, wet years, daily lake elevation, Landsat images that go back to the 70s. We have so much data to work with. It's an ideal natural laboratory. So, as a sedimentologist at least, having all of this data begs the question, can we look at the history of Lake Powell and match it to the sedimentological record in Lake Powell? So can we actually pin specific historical events to specific event beds in Lake Powell? So to further illustrate my point here is a graph that shows the bathymetric profiles of the San Juan River and the lake levels for the accompanying years. So the solid lines at the bottom are the bathymetric profiles starting in 1963 with this purple line, and then you go up through the rainbow until you get to 2017, which is the most recent survey. And then the corresponding lake levels are the dashed lines. So 1963, when the lake was initially dammed, this is the lake level, here's the profile. Looking at this, you can notice two big things. One, that there's been a significant amount of sedimentation in Lake Powell. Here, all through this wedge, and especially here. We're talking, in some places, upwards of 30 meters of sediment here in 56 years. That's incredible. The other thing you can notice is the fact that after this lake level initially rose, there's a significant amount of variation in lake level. So 1986, this yellow line, is one of the highest years in Lake Powell's history. And 2005, this orange line, is one of the lowest years. But even so, you can see that even with these fairly limited years, there are 6 years of lake elevation on here, that's about 30 meters of variation in lake level. That's also significant. So usually, if you're looking at it from a sedimentological perspective, you'd say lake level is probably tied to changes in sedimentation. So if you want to really consider that, you need a record of the sediment, which is where the USGS comes in. Mm-hmm. In November 2018, they took a series of cores in Lake Powell. These are just the ones in the San Juan arm, and there are a lot of them in the San Juan arm, but there are 39 in total, and there is about 500 meters of core to work with. So there's a lot of data in general, both in the history and right here. And this is the longest core that we have in the San Juan, this kind of black rectangle, core 6A, which goes through, if you notice, the entire transition from pre-reservoir to present levels. So it starts below that purple 1963 profile and goes all the way up through the red 2017. So theoretically, it captures the entire sedimentation record. When you zoom in from the 30-meter scale down to the 1-meter scale, this is what I'm working with. Now, there's a scale issue here because some of these beds are centimeters thick, 20 centimeters more, and some of them you're looking at half a centimeter. So it's really interesting to even just go through on a first order level and look at these beds and try to figure out cycles within them. But in general, what I'm doing right now is looking for distinct sediment packages, which are distinguished by color, grain size, sediment structure, and geochemistry. Then trying to correlate those packages that I find with downstream cores along the San Juan River, and then being able to connect those sediment packages to specific events in the lake's history. And that's from geochemical signals and just looking at like where lake level was. So what would I hypothesize to be deposited at this time? But so far, what I've found is that this relationship is a lot more complex than my nice little summary there. And part of the issue with that is that there are two big rivers feeding into Lake Powell, San Juan, which I'm working on, and the Colorado. And the Colorado is the one that's kind of driving everything. So the San Juan is more reacting to events, but there's a lag time that we're not really sure about, and it's kind of difficult to recognize cycles. It's a lot of fun. But with the continued help of the USGS, we just got a bunch of data with the Geophysics, actually. We're going to get that in the next week or two, which will really help out trying to identify all this stuff. We're going to be able to unravel this relationship between lake levels and sedimentation, and really examine more how well sediment stratigraphy principles apply to these cores. Thanks.
For a quick question?
Yes.
When you say Colorado River is driving everything, are you talking about not just water level, but also sediment flux?
Mostly water level. The San Juan supplies its own sediment flux because it would be strange if the Colorado dumped all the sediment and then it went back up to San Juan. That would be really interesting. But mostly just lake level.
So, actually, no, so Colorado doesn't go into the, don't understand.
Okay. Here's the Colorado and the San Juan. So the San Juan Delta is right about here. The Colorado Delta is like around here. So all of the sediment in Colorado goes here. All of the sediment in the San Juan goes here. But then the lake level is mostly driven by the Colorado because it has the higher discharge rates.
So at where they mix, do you have sediment from both river systems?
Good question. We'll figure that out as we go.
Okay. All right, thank you. All right, so up next, he's gonna body slam some science at Joe. This is actually how he does active source seismics. Nick,
Pretty close.
the handlebar Forbes.
All right, I'm Nicholas Forbes. I did my undergraduate here. I did research with Paul Jewell and Keith Coper. But I'm at a first year's master's student doing research on the detection and location of small seismic events surrounding Yellowstone Lake. So, quick summary of this. So you've seen that picture already today. We're utilizing temporary passive seismic methods to generate a data set of earthquakes that maybe a permanent network has missed. So we're going out, actually in 2018, Jamie and a few other folks from the university went out and deployed a bunch of nobles and a few lake bottom seismometers. So we're currently working through that data set. So we're trying to develop a workflow for temporary seismic network detection and processing. And we're hoping to further understand the complex sources that are responsible for seismicity within the Yellowstone Plateau volcanic field. And additionally, we're trying to image hydrothermal features that reside at the bottom of the lake. And I can look through here. All these black dots in here, these are all kind of hydrothermal vents at the base of the lake. And we're hoping to use what we find there as a proxy study for how venting might occur at depth, mid-ocean ridges, things like that. So here's a map of the seismicity in the Yellowstone region. As you can see, it starts at 1959, the Hebgen Lake event, and it runs up to modern time. All the red dots are general seismicity, while all the blue dots are seismicity associated with earthquake swarms, which are quick bursts of events focused in certain areas. But you can see this green box. This is Yellowstone Lake in this region. There's a lot of seismicity in that area. when we look at the faults that run through there, there's three main fault systems. There's the Eagle Bay Fault, on this kind of western central side. The Lava Creek Caldera Margin Fault runs, pretty much to the center, and then the Buffalo Fork Fault right here. And these are all quaternary faults. The USGS data on it says that they slip about 0.2 millimeters per year. But from that past, this map, seeing all the seismicity in the area, we're hoping to maybe quantify that number a little accurately. So the workflow will go as follows. For initialization, that consists of the deployment, retrieval, continuity, and just data quality checks. Next, we're going to apply detection methods. And this will allow us to generate a catalog of events that were maybe missed by the network. And we're using methods like level similarity and template matching to generate this catalog, which will then cross-reference with the University of Utah Seismograph Station's earthquake catalog to see if we missed events, things of that nature. So once we find these events, we'll be able to make our phase picks. Using those phase picks, we're going to use hypoinverse, which is a network standard for locating earthquakes. So we'll take these phase, the arrival times of these phases, run it against the locations of, the seismometers throughout the region, and then we'll be able to get an event location from that. From there, we're kind of going to get into the interpretations. Can seismicity in this region be directly attributed to the existing faults, or maybe something affiliated with the hydrothermal venting? And can we assign mechanisms to these? So, significance, understanding the complex sources of faulting in Yellowstone will allow us to characterize the region and just as a whole. Further understanding Yellowstone is pretty important, as we all know, death, doom, and destruction. Things like that. So understanding also the hydrothermal venting, and hopefully using these as a proxy study for these same structures at depth in the ocean that we can't really reach really well. But future work in this region, or even current work that's going on, is we're going up to do an additional deployment for this project in the summer of 2020. And Jamie is actually going up to do an active source project with about 600 nodal seismometers in a vibro-sized truck to hopefully image the top portion of the magma chamber, figure out percent melt, things like that. He's also working on shallow water microseisms, and then we're working on making a graphic user interface to process these large nodal data sets, so we can just kind of be all encompassing in one area in this project. So, thanks.
On your first map, I noticed that some of the lines seems randomly distributed, while some of the other ones seems to follow linear trend. Is there a known reason for this distribution?
Are you talking about just spacing of all kinds of random areas?
The fact that some of them are on linear trend and some of them are not.
It just depends on the quality of the earthquake location at that point, if you can constrain it directly to an existing fault system.
But not the earthquake, more like if you go back to your first slide,
Yeah, of course.
you say the black dot points where the distribution of the hydrothermal.
Oh, the
is.
hydrothermal, yes. Okay, I see what you're saying now. So these.
Yeah, why is the one on the left bottom corner are following trends, and why the one on the is there because they are on faults?
It's a good guess. I'm not 100% sure on that. But I would assume, because we have the caldera running right through here, right underneath here. So if you have a fault system, that weakens the rock, potentially opens it up to more hydrothermal venting. Would be my guess.
All right, next.
All right. Up next is Claire Atlas. Should save that for the experimentals.
Tagged, I just got my license.
So hello, I'm Claire Atlas. I'm a first-year master's student with Carrie Johnson, and my project will be working on outcrop modeling of delta deposits in Utah and South Africa at the sites shown here. Just as a warning, before I begin, I'll be asking some audience questions, so please participate. This is me. I'm about to pour out a bottle of water. Can anyone here guess where it's gonna go? Down. Down. And I aimed it right to get into the cup. So in this next one, there are a couple of dipping barriers to this. Do you think it's gonna fall in the same way as in the previous picture? No. No, this time, the water flows down. Okay, the last one's real tricky. So here, I've removed a couple key components of the picture. Does anyone know how it's gonna flow or if it's gonna end up in the cup?
I wish.
Yeah, I wish too. And this is the essence of my project, sort of. So I'm looking at delta deposits. So if you look at this seismic line to the right, this is a typical picture of a delta deposit. And in the red box, it's outlined. So you can see the general geometry, but you can't see all the small scale beds and changes in dip and permeability and other things that would divert the flow in uncharacteristic ways. And you can't go look at it because modern deltas are deep in the ocean or other basins. So the only way to look at this is through outcrops as analogs for these inaccessible delta reservoirs. Looking closer at my outcrops, this is a picture of the South Africa outcrop. This is a late Permian shelf edge delta, and this is a really unique place to get to study delta deposits because you get the full basin succession in outcrop. At the very bottom, you have the deep basin fill that's fan sediments. And as you go up the outcrop, you go through the different sections of the delta. And all the way at the top, you have the river channels preserved that were actually feeding sediment into this system. And then with the central Utah outcrop, this is a bit younger. It's late Cretaceous in age, and it's a platform delta. And here, these are the first sands entering the western interior seaway. And how we're going to study these outcrops is we will travel to these sites and collect a lot of high-resolution drone images. And we can stitch these together and make virtual outcrops. And with virtual outcrops, the nice thing about this is then you can map and follow each bed individually all the way through outcrops. You can measure the changes in thickness and dip, and also the changes in the mudstones that cap these sand bodies that really serve as the barriers to flow here. And we can get a good geostatistical understanding of these outcrops. And using all these things, we'll be making fluid flow models. And some things coming out of this project is that we'll have a better understanding of these lateral changes through delta deposits. And then with application to the petroleum industry, deltas are very typical reservoirs, and having a better understanding of fluid flow through them will lead to more idealized well spacing for maximum recovery. And then also we'll have working models for these two sites that can be scaled accordingly to be applied to modern and ancient deltas. And that's everything. Thank you.
Question?
Why these two particular sites?
Well, they're both really classic delta outcrops, and I mean, one of them is pretty close by. We can just get in a van and it's 2 hours away. And with South Africa, we have a lot of work currently going on there on these outcrops. And yeah.
So deltas have a lot of internal geometry that you're going to miss from just using even a really comprehensive outcrop 3D based model. you planning to account for that internal geometry in your flow models, or what kind of flow models are you thinking of using?
So I haven't gotten that far yet, but yes.
Nick will be so excited to talk about flow with you.
Awesome.
Can you use what you see in multiple 2D slices to imagine what might be in between?
Yeah.
Is that the idea? Okay, thank you. And I think that was a grand slam, don't you? Got another one coming up, I'm sure. Kosta Gokas will join us next. Thank you.
Hello everyone, my name is Kostas. I'm a first year graduate student working with Francelin. I did my bachelor's and master's in the Aristotle University of Thessaloniki in Greece, and I also received a scholarship by the Alexander Onassis Foundation for my studies. So my project is called ambient noise beamforming tomography of Salt Lake City using a linear seismic array. First, as you all well know, Utah is one of the states with the highest seismicity. In specific, it's been ranked 6th across the nation regarding annualized earthquake loss, first in the region. On the left, you can see a seismicity map. Most of the seismicity in the state of Utah spans from the north-south intermountain seismic belt, but there are also more faults generating earthquakes. And most of the population of the state is in Salt Lake City, more than 2 million people. So we are interested in studying the shallow structure of the area. Here's where the data from this project come from. They are focused on the east banks of the Wasatch Fault Zone. You can see the geometry with depth based on sketch by the Utah Geological Survey, and you can see that this segment of the fault is the active phase. So we put out stations in this area to study the shallow structure. This is the linear array. It spans across 1700 south, starts from 700 east to 1900 east. This array consists of 32 nodal stations. We have already seen 2 pictures of these stations. It operated for about 30 days across this line, which is 3 kilometers. So we have computed ambient noise cross correlations based on the methodology by Lin. Here you can see a record section for a virtual source on the west side of the array. So when we see these plots, we actually see the wave propagating across the other stations. Here are the receivers. And you can see that at 1 to 3 Hz, we may have seen a move out of Rayleigh waves, but this signal is not that clean, it's not clear. So we have high noise levels, which is super expected in an urban environment. So where other tomographic methods fail because of the high signal, the high noise levels, we have used double beamforming tomography to enhance the signal and simultaneously measure phase velocities. So what we do is that instead of looking at one by one station, we look at areas of source beams and receivers beams to catch up this move out and actually find the true phase velocity for this period. You can see that we use the double beamforming methodology based on Wang, 2019, a former PhD student on the seismic imaging group by Francelin. Based on this methodology actually enhances the signal and allows us to measure phase velocities, and has been successfully applied both on continental scale on Cascadia and on local scale on the San Jacinto Fault. So what we actually want to do is use this methodology and test the applicability in an urban environment. Here's the phase velocity profile that we have got so far. You can see that we catch a slow anomaly around 1 kilometer of the array and a west dipping reflector. Here are also the uncertainties. We actually try to assess the uncertainties from multiple noise sources. And here's the profile overlapped by the geological map of Utah from USGS, and you can see that we have successfully mapped the east bench of the Wasatch Fault, which corresponds to this slow anomaly, and perhaps this west dipping anomaly corresponds with a retrogressive phase of the Provo shoreline. Thank you.
Do you have any other strategies to deal with the anthropogenic waste? Just
Good question. So, the frequency band that we use, 1 to 3 Hz, is super sensitive to human activities. So actually, even a simple drop of coal can be a potential noise source. So we have used uniform tomography that we know that it enhances the signal in multiple scales. So we have tested the probability of this method for now.
Okay, thanks. All right, and I understand that this final study was actually inspired by some experiments conducted at a local Denny's late at night, in which the researcher was observing the fractionation of partially crystallized Aunt Jemima's corn syrup as it percolated through these porous Grand Slam breakfast pancakes. So I think Otto's going to come down and give us the rest of the story. I got that right, didn't I?
So my name's Otto. I did my undergrad at Fort Lewis College in Durango, Colorado, and I work with Sarah and Laura upstairs in the volcanology and experimental metrology lab here. And so what we are interested in studying is how the chemistry of magmas change as they move through the mantle and towards the surface. And so the easiest setting on Earth to do this is at a mid-ocean ridge, due to what we know the most about it there, and its relative simplicity. So at a mid-ocean ridge, we have about 7 to 10 kilometers of oceanic crust, and under that we have down to about 100 kilometers of lithosphere mantle composed out of the minerals olivine and lithospheres. And because these ridges are spreading away, there's a decrease in pressure, and we get adiabatic melting of the upwelling asthenosphere that produces basaltic pillow lavas on the ocean floor. So for a long time, we thought the asthenosphere was composed solely out of one type of rock, known as peridotite. Here's a picture of it. It's composed mainly out of olivine with small amounts of pyroxenes. However, if we look at some geochemistry, and I don't want you to worry too much about this plot, we just have some isotope ratios of epsilon neodymium on the y-axis and a strontium ratio on the x-axis. Essentially, these are all these different colorful blobs correspond to different mid-ocean ridges and different oceanic island lavas. And what each of these blobs represent is the spread of source signatures, so the different source chemistries within the mantle that we're melting. And so you can see the spread is quite large. So what some authors have proposed recently, along with Sarah, is that we're not only melting one rock type, peridotite, we're actually melting a completely different lithology within the mantle called pyroxenite as well. So in order to understand if we are melting pyroxenite in the mantle, and how much of it, if we are melting it, we're melting, there's some complications with analyzing the chemistry of the surface since we can't actually go down there. So this is a cross-section of a mid-ocean ridge, and let's say we have a magma that's generated at the bottom of the mid-ocean ridge. That magma is going to be composed of different types of elements, and some of those elements are going to be incompatible. That means they like to be in the liquid or the melt phase. And other elements are going to be compatible. That means they like to hang out in the crystal with the crystal structure of the solid phase. So as that magma rises to the surface, the incompatible elements, they're going to be happy in the liquid phase and they're going to go faster, whereas these compatible elements, they're going to end up hanging longer in the within the channel migration. And this effect is known as manochromatography, similar to what you experience in the chromographic column in a chemistry class. So you end up oftentimes with this overestimation of the abundance of incompatible elements at the surface, which makes it really hard to tease out any source signatures we had down here. So we are trying to combat this problem with an experimental setup where we're using one atmospheric furnace that's located upstairs on the 4th floor. Within that furnace, we have a melt reservoir, which represents the magma that would have been generated at the base of the spreading center. And then we have a silicon matrix that represents our mantle. So this is going to be composed mainly out of olivine and pyroxenes. So we then use gravity to push this melt reservoir, this magma, through the silicon matrix. In effect, we're getting the reverse direction of what, modeling the reverse direction of what's happening at a mid-ocean ridge. And then we can then sample that at different times by quenching it and analyzing its chemistry. So then we can do that at a different time, allowing more melt to percolate through the silicon matrix, get another sample, and this will enable us to get a chemical evolution of how the chemistries of these melts are changing as they rise upwards through the mantle to the ocean floor. So what we're trying to do is we can vary different parameters with our experiments, and that's going to enable us to hopefully identify what sort of parameters preserve certain signatures of different lithological sources within the mantle, and eventually hopefully be able to identify the signatures that represent pyroxenite or peridotite. And if we do that, we'll be able to get a better understanding of the composition of the outer mantle. And since pyroxenite is actually the equivalent of subducted oceanic crust, this plays an important role in understanding how much subducted oceanic crust is actually moving around in the mantle, and helps us with our understanding of convection and mantle dynamics. That's it. Thank you.
So, based on the picture you showed of the setup, it's really small scale. Do you have a way to ground truth or set expectations for how the system should behave, just so that you know that this experimental setup is behaving sort of close to, like, order of magnitude level true to life?
Yeah, so that's challenging to do because we can't actually directly sample anything down here, but we do have like chemical analyses of lavas collected in mid-ocean ridges. A lot of this, similar experiments have already been done that kind of shows that you get similar results to what you would expect in these types of situations.
Are you varying the chemistry of your melt reservoir and your matrix?
Yeah, so we're going to do that systematically. We're going to vary the chemistry of the melt with the same matrix, and then do the vice versa. So.
Does the pressure regime have any effect on this, since you're doing this at sea level, basically?
Yeah, so it has very little effect on the actual chemistry that's going on. Some of the elements, like the distribution coefficients where the elements are pressure dependent. But if we're just looking at the difference between super incompatible elements and compatible elements, that difference doesn't actually change depending on pressure.
Okay, thank you.